Example 9.3. In 1996, the Space Shuttle Columbia deployed a tethered satellite on a wire out to a distance of 20 kilometers. The wire was oriented perpendicular to the Earth's magnetic field at that point, and the magnitude of the field was B equals 5.1 times 10 to the power negative 5 Tesla. Columbia was traveling at a speed of 7.6 kilometer per second. Question wants us to find what was the potential difference induced between the ends of the wire. So let us first write down what is given to us. We have the length of the wire, which is 20 kilometer. So I write the length L equals 20 kilometer, which is 20 times 10 to the power 3 meter. 1 kilometer is 1000 meters. So I multiply with 10 to the power 3, which is 1000. Then I have the magnetic field B, which is 5.1 times 10 to the power negative 5 Tesla. And then we have the speed V, which is 7.6 kilometer per second. Convert this to meter per second. So we know that 1 kilometer is 10 to the power 3 meter. So this is how I will convert kilometer per second to meter per second. And the wire is perpendicular to the Earth's magnetic field. So I will take my angle theta to be 90. They want me to find what is the induced potential difference. So what is delta V induced? Now this is a case of motional EMF, where you have a wire which is moving inside a magnetic field. And for motional EMF, the induced potential difference is equal to the product of magnetic field B, the length of the wire, and the speed with which the wire is moving, which is BLV. So let's substitute the value. Magnetic field B is 5.1 times 10 to the power negative 5. The length of the wire is 20 times 10 to the power 3. And the speed V is 7.6 times 10 to the power 3 meter per second. And when you solve this, you get the induced potential difference to be equal to 7752 volt. And if you want to round this off to two significant figure, because all the other quantities in the question is in two significant figure, you can write this as 7800 volt. So this is my induced potential difference between the ends of the wire. Example 9.4. A conducting rod is pulled horizontally by a constant force of magnitude F equals 5 Newton along a set of conducting rails separated by a distance of A equals 0.500 meter. The two rails are connected and no friction occurs between the rod and the rails. A uniform magnetic field with magnitude B equals 0.500 Tesla is directed into the page. The rod moves at constant speed of 5 meters per second. We need to find what is the magnitude of induced potential difference in the loop created by the connected rails and the moving rod. So here you have a set of conducting rail which is connected by a movable rod. So this setup of the rod and the rail forms a loop, and when the rod moves, the area of the loop changes. And since it is moving to the right, the area in our situation is increasing. And we need to find what is the induced potential difference in the loop created by connected rails and the moving rod. So let us first write down what is given to us. We have the force F with which the rod is being pulled, which is 5 Newton. Then I have this separation between the rails, which is A equals 0.500 meter. Then we have the magnetic field B, 0.500 Tesla. And I have the speed V with which the rod has been moved, 5 meters per second. I need to find the induced potential difference. From Faraday's law, we know that the induced potential difference is equal to the negative of rate of change of magnetic flux. The magnetic flux phi can be written as P A cosine theta, where theta is the angle between the area vector A and the magnetic field P. Whenever you have an open loop, the area vector is always perpendicular to the surface of the loop. And in our situation, this area vector is in the same plane as the magnetic field. It's along the same line as your magnetic field, since magnetic field is also perpendicular to the loop. So since both the area vector and magnetic field are perpendicular to the loop and they are along the same line, we take the angle theta between them to be equal to 0. So I can write my magnetic flux to be equal to B times A, since cosine of the angle 0 is 1. Then if I have to find the induced potential difference, I need to take the derivative of this flux, the rate of change of flux, which is d phi by dt. Since magnetic field is constant, you cannot differentiate that with time t. We will keep it as a constant outside. And we will only take the derivative of the area since the area is changing with time t. Now, how do we find this area? We can write the area A as the sum of two parts. First, the area A0, which was the original area before the rod started moving, plus the area delta A, which is the increase in area when the rod started to move. Then we write A equals A0 plus the increase in the area of the loop can be written as length times the width. The width is constant since it is the distance between the two rails, which is A, and I can find the length by multiplying velocity with time t, because we know that distance covered when an object is moving with speed v is just the speed times the time t. So I get the new area as original area plus A times v into t. Then we take the derivative of this area to substitute in my value for induced potential difference. Since the original area is a constant, the derivative of a constant is 0 plus derivative of just t is 1. So you are left with A times v. So I can write for d phi by dt to be equal to b times A into v. And the same thing I will substitute here. Then we write the magnitude of V induced to be equal to the magnitude of negative d phi by dt, which is equal to BAV. When you just take the magnitude, just the value, you can remove the negative sign. Now substitute magnetic field is 0.500 Tesla times A is also 0.500 meter and the speed V is 5 meter per second. And when you solve this, you get the induced potential difference to be equal to 1.25 volt. Now, this example over here is also a case of motional EMF. Because here again, you have a rod which is moving inside a magnetic field. So whenever you have a wire, a straight wire or a straight rod moving inside a magnetic field, you can directly use the rule of induced potential difference to be equal to magnetic field times length times the speed of the wire. So you don't need to derive all of these things even when the area is changing. If for a given loop, only one part of the loop is moving and that part is a straight conductor, then you can use the case of motional EMF to solve the problem. As you can see, this rule is similar to BLV, where A is the length of the conductor. So if you have a case like this, you can directly use the rule induced potential difference equals BLV to solve the question.